Section 6.2 is all about volumes. And we would like to be able to find the volume of any type of solid. Now, if we have something like a cylinder, a right circular cylinder, or a rectangular box, we know exactly what the volume is. Maybe you even remember from Calc 1 when you have a cylinder, volume is equal to 1/2 pi r squared h, because the area of the base is equal to pi r squared, and then this is the height, so area of base. Same thing if you have a box. Yeah, I don't know why I'm trying to draw a box, but the volume is equal to length times width times height. This is the area of the base times the height. That works for any cylinder. A cylinder is just a solid that has sides that are straight up and down. For example, I have my glasses case here. Assume the sides are straight up and down. If I knew the area of this base, then I could find the volume of this glasses case just by multiplying the area of the base times the height. But the things we want to find the volumes of are not straight up and down always. So we have to think about dividing them into slices. So we slice them up and find the volume of each little slice and add those up. Now, the more slices you have, the more exact your volume is. What does that make you think of? Riemann sums. Just like when we were dividing the area up into rectangles and then we added them up and let the limit of the number of rectangles go to infinity, we get an integral. We do the same thing to find volumes. So here's the pretty picture. We do some slices along the sides. So if we want to add it up, we take the area of a slice times delta x, which is the thickness of a slice, kind of like the area of this base times the height. And then we add them up. And here's our definition of volume. It's a cross-sectional area. We divide it into slices and we add up the volume of each of those little slices. And we're going to start with simple ones whose cross-sections are all circles. And we get these as solids of revolution. So we can take a region and revolve it around a line. So suppose we had a half circle. We take that region and we revolve it around the x-axis. We end up with a sphere. So we are going to use that definition for volume to prove that the volume of a sphere is 4/3 pi r cubed. I'm going to take a minute and write some stuff down. So I went ahead and wrote down what we're trying to prove. I know that the equation for a circle with radius r is x squared plus y squared equals r squared. I'm just going to take this semicircle, the top half, and revolve it around the x-axis, just like I did my little thing here. Boom, revolve it all the way around the x-axis, and then I'll have a sphere. So this is y equals the square root of r squared minus x squared. And then we revolve it, and I'm going to make slices all along the x-axis. I'm going to go ahead and dash this in as if I have revolved it all the way around the axis. And then I'll make these slices here, and each slice is a circle. And the radius of each of these circles is y. So when x is equal to r right over here, the radius is equal to r squared minus r squared, which is 0. As x gets bigger or smaller, closer to 0, the radius gets larger. Here, where x is equal to 0, the radius y is equal to r. So you see that it works. We got exactly what we want. So each slice is a little circle. Radius is equal to y, which is the square root of r squared minus x squared. So the area of one of these slices is pi r squared, which is pi times y squared, so pi times the square root of r squared minus x squared squared, which is pi r squared minus x squared. So my volume is going to be equal to the integral from one end to the other. So from negative r to r, because I'm going to make slices from one end of my picture to the other. The area of each slice is pi r squared. So pi times r squared minus x squared. And for the height of each little one, we think of the thickness, and that is just represented by dx. So this would be pi times r squared times x minus x cubed over 3, evaluated from minus r to r, and I'm going to do that on the other side of the paper. So I copied it over again just so I wouldn't forget what I was plugging into. I plug in the positive r, I plug in the negative r, and I end up with 4/3 pi r cubed, just like I expected to. Now, you could have taken advantage of symmetry, because if you have this circle here, you could look at just half of the circle and double it. So you could have gone just from 0 to r and doubled it like we did on the PowerPoint. And there's the pretty pictures. So the slabs are discs. So this brings us to the volume for any solid of revolution. If we revolve something around a line and we get a circle, we get solid discs. It's just pi times the radius of that circle squared times the thickness. Now let's look at example 2. We want to find the volume of the solid obtained by rotating the y equals square root of x from 0 to 1. So I'm going to set it up for us. And you are going to have to be able to draw a simple region. I won't expect you to draw anything terribly complicated. But square root of x, yeah, you should be able to draw that when going from 0 to 1. So that's important. You need to know where you're going along the axis of rotation. So our axis of rotation is the x-axis. And I usually draw myself a little circular arrow around the axis of rotation. Here's my y equals the square root of x that I made from one of those little twirly balls. And we take that and we revolve it around the axis of rotation. And we end up with something that looks kind of like this little bullet. Here, I'll see if I can put it under there. There you go. Looks kind of like a bullet or a lampshade. So, each slice is a circle because we've gone around. And the radius of each slice, the radius of a slice is equal to the y-coordinate, just like it was before. But in this case, y is equal to the square root of x, which means the area of a slice is equal to pi times the square root of x squared, pi times the radius squared. So let's simplify that. That's just pi times x. And then my volume would be equal to the integral from one end to the other. So we're making slices from 0 to 1 of pi times the radius squared, or the area. So pi times x dx. And that one's so easy. We just have pi times x squared over 2 evaluated from 0 to 1. And you are savvy enough to know that when you plug 0 in, you get 0, and you end up with just pi over 2. And there's the pretty solution. Now, if we have a hole in the middle, then instead of having just a disc, we have a washer. And a washer is like a disc with a hole in the middle. Now let's look at practice number 1. We want to find the volume of the solid obtained by rotating the region, and we want to sketch the region, the solid, and a typical disc or washer. So if I were going to sketch this solid, I would just add in the little bullet-shaped area there. Let's look at this one. We have y equals e to the x. This is practice 1. Y equals 0. X equals minus 1. And x equals 1 about the x-axis. So step number 1 is to sketch your region. I know that x is going to go from minus 1 to 1. So we'll go from minus 1 to 1. E to the x, well, e to the minus 1 is something tiny. I know e to the 0 is equal to 1, and then e to the 1 is 2.7 something. You don't have to be exact. Just do the best you can. So we want the area bounded by x equals minus 1, x equals positive 1, y equals e to the x, and y equals 0. So there's my region. I'm going to revolve this about the x-axis, which means my solid looks something like that, and a slice looks something like that. So your pictures don't need to be any better than that. If you can draw a picture that good, then you're fine. So we have a bunch of circles here. Let's find the radius of a circle. The radius of a circle, since we're revolving around the x-axis, is just y. and y is equal to e to the x. So the area of a slice is pi times the radius squared. So the volume is the integral from one end of the slices along my axis of rotation to the other. So negative 1 to 1 times the area, pi times the radius squared, which is just pi over 2e to the 2x, evaluated from negative 1 to 1. So pi halves times e squared minus e to the minus 2, which pi halves times e squared minus 1 over e squared. You could have left it like that. You need an exact answer. That would be fine. You can plug it in your calculator and be sure you have it right. Example 3 is a little different. This time we're revolving around the y-axis instead of the x-axis. So let's start just by drawing our own picture. I know there's a really pretty one over there, but we're going to practice. We know what x cubed looks like. It increases really quickly. So I'm going to make it look like that. Y equals 8. So here's the line y equals 8. X equals 0. That's the y-axis. So this is my region right here. And I'm going to revolve about the y-axis. So it looks kind of like a tulip. And here's my slice. So here's my beautiful cubic. I revolve it around the y-axis and it opens up and looks something like that. If I slice it, I'm slicing along the y-axis. So right here, here, here. My slices are going this way. So my limits of integration are going to go from the bottom at 0 to the top at 8. I need the area. Well, since I'm going around the y-axis, my radius is equal to x. Ooh, it says that y equals x cubed. Well, if y equals x cubed, then x is equal to y to the 1/3 power. I need to integrate with respect to y because my slices are along the y-axis. So r is equal to x, which is y to the 1/3 power. That means that my area of a slice is equal to pi r squared, which would be pi times y to the 1/3 squared, which is pi y to the 2/3. So we're going to integrate from 0 to 8, pi y to the 2/3, and the thickness of the slices are represented by dy. So all I have to do is add 1 to the exponent, divide by the new exponent, and plug numbers in. I went ahead and rewrote it on the other side. I added 1 to the exponent, divided by the new exponent. You can plug 8 to the 5/3 into your calculator and get 32 out, Or you can think about the cube root of 8 is equal to 2, and then 2 to the 5th power is 2 times 2 is 4, 8, 16, 32. So you end up with 96 pi over 5. So again, these are just discs. We haven't done any washers yet. There's the pretty answer. This one's also going to be discs. So set this one up and give it a try on your own. Then we'll come back and compare. So how'd it go? My picture on this one is particularly bad because this should really have gone out further, but that's okay. I did the best I could. You can kind of see that it looks kind of like this because we started with a little side that looked like that and we spun it around the y-axis. So we had to have a function with y's in it because we're integrating with respect to y. Our slices go here along the y-axis. Each radius is equal to x because we're slicing along the y. So x is equal to y squared over 2. I just isolated that x there. So area is pi r squared. So pi times y to the 4th over 4. And then it's easy integrating. You could have done that last semester. Now, let's add in another little twist. We're going to do washers. So we'll find the region between two curves so that we end up with a hole in the middle. So let's look at example 4. We want the region enclosed by y equals x and y equals x squared, and we'll rotate it about the x-axis. So it's like in 271 when you had to find the area between two curves. First thing you needed to do is figure out where they intersect. So for example 4, if we're going to take that region and revolve it around an axis, we need to know where they intersect. And that can help you draw that region too. So y is equal to x and y equals x squared. So we set x squared equals to x, then x squared minus x equals 0, because that's how we solve quadratics. We get everybody on one side of the equal mark, factor, set each factor equal to 0. So, and this one you could have figured it out without doing all that algebra, because we have y equals x, which is just the identity line, and y equals x squared, which is just your generic parabola. So this is right there at 1, where they're exactly the same. We're revolving it about the x-axis. And let me get rid of that line. I don't want that there. I'm going to take this, and on the outside it's going to look just like a cone, but it's going to have kind of a bubble on the inside. And here's your pretty picture. You can see that a slice out of that looks like a disc with a hole in it, which is known as a washer. So for this one, just like you did top minus bottom when you did the area between two curves, you're going to do the big radius minus the little radius. So you'll be taking the area of that big disc and then subtracting out the little hole in the middle. So I usually call the big radius, the outside radius, capital R. And we just look at it. the one that's furthest from the axis of rotation. My axis of rotation is the x-axis, so my outside radius is equal to x. Little r, my inside radius, is equal to x squared. Because, again, the radius when you're going around the x-axis is equal to y. And we want to integrate with respect to x because that's our axis of rotation where we're making our slices to make our washers. So the volume is going to be the integral from one x-intercept to the other, so the x's go from 0 to 1. Pi, we do the outside radius squared minus the inside radius squared. So not bad, we just added one extra little piece to it. So we have pi integral 0 to 1 x squared minus x to the 4th. I like it when they just go from 0 to 1 because that makes it easy to plug in. We have x cubed over 3 minus x to the 5th over 5 from 0 to 1, which gives me pi times 1/3 minus 1/5 minus 0. And let's see, 1/3 would be 5 over 15. 1/5 would be 3 over 15. So this would be 2 pi over 15. Let's see if I got the arithmetic right. Yay, I did. Your turn. Give practice number 3 a try. This time we're going about the y-axis. So you'll need to have your functions in terms of y, and they're already ready already. So how'd it go? First thing I did was to graph these two things. I knew that this was a parabola that opened to the left, and if I plug y equals 0 in, x equals 2. So I know it hit the x-axis right there. I also could have figured out that it crossed the y-axis at plus or minus 2. Let's see, actually plus or minus square root of 2, because I would need that to be equal to 0. But I set them equal to each other, and I find that they cross at plus or minus 1. Oh, and y to the 4th just looks like a parabola that opens to the right, except it's flatter because it's to the 4th power instead of the 2nd power. So I set them equal to each other. It factored like this. This one has no real solutions. So I looked at this piece and found that y is plus or minus 1. Then I looked at the distance to my outside function. So my outside radius is the 2 minus y squared. My inside radius is the x to the 4th power. So my volume is equal to the integral, and remember, we're going along the y-axis this time as we make our slices. We go from minus 1 to 1 of pi times the outside radius squared minus the inside radius squared. And then I took advantage of the fact that it was symmetric. So if you can take advantage of symmetry, do that. Parabolas and even exponents do that. So I changed it to 2 pi, the integral from 0 to 1. I did some algebra there, and then I did some simple integrals and got the exact answer. Now, We're going to add another little complication in here. We're going to revolve around something that's not the x or y axis. Now, let's look at example 5. We want to find the region enclosed by the curves y equals x and y equals x squared. Okay, that's not bad. Example 5. We know what that region looks like, so let's quickly do that region. So there's y equals x and y equals x squared. Here's my region, because we just drew that a moment ago. So we know that that's going to go from 0 to 1. But we want to rotate it about the line y equals 2. So think about which axis that's parallel to. Y equals 2 means I don't care what x is equal to. I'm always 2 units up. So there's the line y equals 2. It's parallel to the x-axis. That means if I'm making slices along the axis of rotation, I want to integrate with respect to x. Here's my axis of rotation. So it's going to look like this. And let's get rid of this. Say we have something that looks like that. Again, your pictures don't have to be great. They just have to help you visualize what's going on. You can see the picture that the authors created is way better than mine. But you can tell what's going on. It's like a bubbly lampshade. So, this time we're going to do the same things. We need to find an outside radius and an inside radius. My outside radius is the distance from my line to the squared function. So the one that's furthest away from the axis of rotation. Your distance is always going to be bigger minus smaller, top minus bottom. So 2 minus x squared. So if you need to check and be sure you have it right, when x is equal to 0, the radius is 2. When x is equal to 1, the radius is equal to 1. That's right. Little r is going to be the distance from the axis of rotation to the curve that's closer to the axis of rotation. So 2 minus x. So now my volume, my integral is going to go from 0 to 1 because we already know that's what's enclosed between x squared and x. Pi times the outside radius squared minus the inside radius squared. You don't need to watch me do algebra. So you square those things, you combine them, and you end up with 8 pi over 15. Now these you could, most of them on your test I'm going to allow you to plug in your calculator. I'll make you do a couple by hand just to be sure you're not out of practice. But most of them you can just plug in your calculator. And when you do that, I encourage you to not put the pi in when you plug it in your calculator, and then just put the pi on at the end. Okay, practice number 4 is for you. So give it a try, and then we'll come back and compare answers. Again, our line is y equals -1, which is parallel to the x-axis. Okay, I truly struggled with the picture on this one. not sine and cosine, but trying to revolve them about the axis. So really I redrew it over here because it made it more clear to me which was the outside radius, which was the distance from cosine to -1, and the inside radius, which is the distance from sine to -1. So again, you do top minus bottom, so cosine minus -1, which makes sense because you're adding 1 to the distance, so you end up with cosine plus 1 and sine plus 1. We did some squaring. We used the half angle formula. And if you knew the double angle formula for cosine, you could have used that, but I just used the half angle formula. And we ended up with cosine 2x, 2 cosine minus 2 sine. We integrated, and we got an exact answer. That would be a reasonable test question for you to remember how to do by hand. So don't forget those trig integrals. Okay, let's do an example where we revolve two things about a line parallel to the y-axis. Now, example 6, we have y equals x and y equals x squared again. So, yay, we like that. So I'll do that real quick, x and x squared, about the line x equals -1, which lives over here, x equals -1. So we have y equals x and y equals x squared. Here's my region right here. I'm going to have an inside radius and an outside radius, but I'm making my slices along this axis of rotation. So they are going to go from 0 to 1 because they cross at the point 1, 1. So we're going along the y-axis. My radius is equal to the x-coordinate. So x equals y and x equals the square root of y. So outside radius is going to be the distance from the square root of y. And we do right minus left because it's always bigger minus smaller. So square root of y minus -1, which is square root of y plus 1. And my inside radius is just y minus -1 or y plus 1. So volume is going to be the integral from 0 to 1 pi times the outside radius squared minus inside radius squared. And there's the pretty picture. And you'll notice I like to just kind of draw the region that helps me to visualize the outside radius and the inside radius. But we squared it, we did the integrating, and we end up with pi over 2. It's a lot of work for pi over 2, but that's what we get. And now it's your practice. So give this one a try. Remember, if x times y is equal to 1, then x is equal to 1 over y. This one took some extra work because we had to divide it into 2 pieces because it looks different from y equals 0 to 1/2 than from y equals 1/2 to 1. From 0 to 1/2, it just has straight edges. So I did that piece separately. I had an outside radius of 3 and an inside radius of 2, and it was easy. From 1/2 to 1, I had an outside radius of, and I did it on my non-3D picture here, 1 over y to -1, and then an inside radius from 1 to -1, so an inside radius of 2. So then I had to do that multiplication and that integration, and I ended up going through a lot. And you could have rewritten this as 2 pi times the ln of 2 instead of -2 pi times the ln of 1/2 because of the laws of logarithms. But if you got that far, then hey, I'm really happy. That's awesome. Okay, let's look at example 7. Example 7 is a little different. It's not a solid of revolution. This time we want to determine the volume of a solid with a circular base of radius 1, parallel cross sections perpendicular to the base are equilateral triangles. So these are hard to picture. You really have to think about them. So the volume of the solid with a circular base of radius 1. Its base is just a circle. Parallel cross sections are equilateral triangles. So when you slice it, instead of getting circles, you get equilateral triangles. So I'm going to take a minute and try to draw a picture of this to help you picture it. Actually, trying to draw it yourself really helps you to wrap your head around what's going on. So first thing I did is I put the XY plane flat on the sheet of paper, and this is my flat circle, and I imagine that there are equilateral triangles above it, and each equilateral triangle has sides equal to the width of this circle. So they're sitting above it. Now I'm going to take a 2D image of x squared plus y squared equals 1, because that's the circle with radius 1. So here's the x-axis, and as I slice, I'm going to get a triangle for each slice. And each triangle has a base equal to the distance across that circle. So if this is one of those triangles, the base goes from -y to +y. So the length of the base is equal to 2y. But if we want the area, then we need the height. So this is equal to 2y because it's an equilateral triangle, 2y. So this is y. The hypotenuse is 2y. If I need to know what the height is, then y squared plus height squared is equal to hypotenuse squared, so 2y squared. So y squared plus h squared equals 4y squared. So the height, so what did I have written down? I had y squared plus the height squared equals 2y squared. Y squared plus h squared equals 4y squared. So the height squared is equal to 3y squared. So the height of each of these triangles is equal to square root of 3 times y. I am making my slices along the x-axis. So since x squared plus y squared is equal to 1, This implies that y squared is equal to 1 minus x squared. So y is the square root of 1 minus x squared. We're getting there. So, area of a triangle is equal to 1/2 of the base times the height. The base was equal to 2y, and the height was equal to square root of 3 times y. So this would be square root of 3 times y squared, and oh good, y squared is just 1 minus x squared. I don't have the radical in there. So my volume is going to be equal to the integral from one end to the other. And remember, we were slicing along the x-axis here. So we're going from -1 to 1. 1/2 of the base times the height. So area, 1/2 of base times height is square root of 3 times 1 minus x squared. And again, you don't need to watch me do arithmetic. It's right here. 4 times the square root of 3 over 3. Okay. I'll help you set up practice number 6, because it's another one of these solids that is not a solid of revolution. We have the base of S is a circular disc with radius r, parallel cross sections perpendicular to the base are squares. So this is practice 6. So let's put my x and y axes here. And the base is a circle with radius r. So here's my circle. X squared plus y squared equals r squared. We'll call this x and this y. And parallel cross sections are squares. So we have squares sticking up that are as wide as my circle. And then smaller squares. And there's the pretty picture, but again, I think trying to draw it yourself helps you to wrap your head around it. So now let's look at x and y oriented the way we're used to. X squared plus y squared equals r squared. We make a slice right here. That means the area of a square is going to be 2y is the length of one side, and the other side is also 2y because it's a square. So area is equal to 4y squared. But since we're going along the x-axis, y squared is equal to r squared minus x squared. So my volume is going to be equal to the integral from one end to the other, negative r to r, of the area of a square. And the area of a square is 4 times y squared, r squared, minus x squared, dx. So I'll pull 4 out, r squared x minus x cubed over 3, evaluated from negative r to r, gives me 4 times r cubed minus r cubed over 3 minus minus r squared minus r cubed over 3, and that would be minus. I'm going to pause and do the arithmetic and get back to you so you don't have to watch. This one reminded me of that sphere that we did, except it's bigger because it has squares instead of just a sphere. So we ended up with 16r cubed over 3. Now you try to do this one on your own. Practice number 7. The base of the region enclosed by the parabola y equals 1 minus x squared in the x-axis. Okay, you know how to draw that. Cross sections perpendicular to the x-axis are squares. So again, the area of a slice is just going to be length times width. Give it a try. Now this one you had to integrate with respect to y because your slices are perpendicular to the y-axis. So you needed to rewrite your function in terms of y. But when you draw your squares in, like I drew this one that's at the bottom, it's 2 units wide and 2 units tall. So this one is 2x units wide and 2x units tall. So I had to rewrite x in terms of y, and then the area of one of these squares is 2x squared, so it would be 2 times the square root of 1 minus y squared, which you end up with 2. So, a lot of stuff. Take your time, be patient, draw your pictures, do the best you can. You've got this.